My name is Anders Hejlsberg. I'm a technical fellow at Microsoft, where day-to-day I work as the chief architect of the C# programming language, and I also participate in the development of the .NET framework and oversee sort of all of our programming languages efforts. And I'm here to give you, I sort of think of it as a brain dump of the things that influence us as we think about designing programming languages for the next 10 years or 5 or 10 years. You know, where is C#, where is VB going, where is F# going, what is it that influences us? That's what this talk is about. And since it's a talk that sort of is about the future, I thought I wanted to start with a historical perspective. Some of you may have heard of this product. This is a product I worked on about 27 years ago called Turbo Pascal. That's how I got my entry into the field, and I thought I'd just take a couple of minutes to show you what programming looked like back then, and then we can debate how far we've come since. So let me just actually. I actually have turbo.com on my machine here. It's all of 39K, and it actually works. So let's try and do a little bit of coding here. We'll include error messages, yes. Oops. Let's make a program called hello.pass here. Program hello. Colon. Integer. Begin for I colon equals 1 to 10 do right len of hello world. There, a little program in Pascal. Let's try and run that. And whoops, I made an error here. And look, this was actually very new back then. It took you to where the error was. You didn't have to first put in another floppy and start the editor and whatever. So let's go change the syntax error here to single quotes. And let's run. And there we go, running. And that as well was new, the sort of integrate. Thank you. Yes. It's actually quite amazing that it still runs on this box after 27 years. Now, a lot has happened in the hardware since then. The machine that I used to write Turbo Pascal on was a Z80-based 8-bit computer with 48K of RAM. You know, since then, the machine I have here has about 100,000 times the external storage, 10,000 times the amount of memory, and a CPU that runs about 1,000 times faster. Yet, if you look at what's happened to the software since then, how much better have programming languages really gotten in 27 years? Interestingly, if you look at the C# version of this program here, it's one line longer than the Turbo Pascal version, and so you know it sort of brings a couple of things into focus. First of all, programming languages obviously evolve slowly, you know, and let's see. Okay, yeah. Let me go to the next one. So sorry, I lost my train here. So programming languages obviously evolve rather slowly. You know, something, of course, has happened. You know, we've gotten object orientation and whatever into it, but they definitely haven't gotten 1,000 times better. You know, but on the other hand, you can wonder then, well, where has all of this capacity gone? And it's actually, in my view, not so much gone into the programming languages, but it's gone into the frameworks and the tools. If you look at the size of the frameworks that we have today, they are about 1,000 times larger. You know, the runtime library that came with Turbo Pascal had about 100 functions in it. Now, if you look at the .NET framework, we have about 10,000 classes in there with about 100,000 methods in it, so it's 1,000 times larger. Likewise, if you look at the IDEs, we have all sorts of wonderful features now, like colorization and statement completion and refactoring and debuggers and profilers and so forth. A lot has happened here. So programming languages clearly evolve slowly is one of the things we can take away from this. Another thing I think we can take away is the importance of these frameworks like .NET or Java, and the tremendous value that they bring to the table. And sort of what we're seeing now is that programming languages tend to now build on top of existing frameworks instead of start from scratch. Most of the new programming languages that are coming out these days, like F#, for example, or if you look at in the Java space, Scala and Clojure and whatever, they're all built on top of existing frameworks because there's so much to leverage there, and it's simply too expensive to start over every time. So one of the things I think that has been true for the entire time that we've had programming languages, the last 50, 60 years, is that we keep raising the abstraction level. We keep making our programming languages more expressive, more succinct, so you can do more with less code. In a sense, we started out with assembler, then went to procedural programming languages like Pascal and C++, and then on to Pascal and C, then on to object-oriented languages like C++. And now I'd say we're sort of in the managed era. Managed execution environments like .NET and Java with garbage collection, type safety, exception handling are now all sort of core aspects of the platform. And I see no indications that this trend is going to stop. So I think we're going to continue to see higher and higher levels of abstraction, and the challenge for us as language designers is to understand and define what those next levels of abstraction will be. And I think there are today probably three major trends that influence us there. There's first a sort of move towards more declarative styles of programming, and here specifically I would mention phenomena such as domain-specific languages and functional programming. And then in the last 5 years, I think we've seen a dramatic resurgence in dynamic programming languages. And that definitely influences us as well. Dynamic programming languages have great meta-programming capabilities, and there's a bunch of interesting stuff happening in the JavaScript engine wars right now. And then, of course, there's concurrency. The whole multi-core, many-core revolution is foisting concurrency on us, whether we want to deal with it or not. It's something that we have to take into account. Also, I would say that as programming languages go, the traditional taxonomies of languages are sort of breaking down. It used to be that you were either an object-oriented language or a dynamic language or a functional language, but more and more we're seeing these sort of silos break down and languages pick paradigms from each other. Static languages are getting dynamic typing, dynamic languages are getting static capabilities. All of the major languages are influenced by functional programming these days. So more and more, the new trend is multi-paradigm programming languages. Okay, so for the rest of the talk, I'll try to drill into these three buckets in a bit more detail, starting with declarative programming. So today, when we write our applications, we by and large use very imperative programming languages like C# or Java or C++. And what characterizes these programming languages is that when you write your programs, it is of course about the what you want done, but it is also in excruciating detail about the how. We are very, very almost over-specific in our solutions to the problem. You know, you write your programs with for loops and if statements and a sub I equals a sub I plus 1 and whatever, and you're just this whole machine that moves data around. And by the time, you know, first of all, this of course makes programming rather tedious at times, but also it makes it very, very hard for the execution infrastructure to be smart about running the program. You know, by the time you've written an imperative program like this and compile it into IL and you give it to the VM to execute, there's not a lot the VM can do to try and be smart about it. It has to just follow the instructions one by one. You know, if we wanted to, like, for example, try to parallelize the program, it's very hard because the higher meaning of it has sort of gotten lost in it's all about the how, and we can't really tell what the what was in the program. So there are a couple of ways that we can move towards more declarative styles of programming. What we really need to do is get to styles where we say more about the what and less about the how in our programs, so the execution infrastructure can be smarter about adaptively running it and taking into account, you know, how many CPUs you have and what kind of hardware you're running on and so forth. And as I said earlier, I think there are two sort of important developments there that can help us. One is domain-specific languages, and the other is functional programming. So domain-specific languages are really nothing new. In a sense, we use them every day in our applications. Examples are SQL or CSS or regex or more specific ones like Mathematica or Logo or what have you. You know, little languages that are intended for specific domains as opposed to general purpose programming languages. The definition to sort of, or there isn't really an exact definition of what constitutes a domain-specific programming language, and I'm not going to venture in here to try and give one. You know, is UML a domain-specific language, even if it doesn't have a syntax and whatever? You know, I don't know, but I'll give you some thoughts about what I think is important. A fellow named Martin Fowler has this sort of taxonomy of domain-specific languages. He divides them into external DSLs and internal DSLs, and I think that's actually sort of a pretty meaningful division. External DSLs are languages that are contained in themselves. They have their own syntax, their own parsers, their own lexers, and so forth. They're like little mini programming languages. They might even have their own source files that sit next to the general purpose programming language. And that contrasts with internal DSLs, which really is just sort of a fancy name for modern APIs and their usage patterns. And I'll show you some examples of that. First, here are some examples, though, of external DSLs. We have like XSLT, there's some SQL, and there's some Unix script on this particular slide here. What characterizes an external DSL, in a sense, is that to create one, you really sort of have to be a programming languages designer. It's not for you know, the everyman to do these. It's more the exception than the rule to create them. External DSLs tend to be great at their particular domain, and then they tend to kind of suck at everything else. You know, James Gosling at one point sort of put it like, you know, every configuration file ends up being its own programming language, because you start out with just a few little things you can say, but then, I also want to have rules in there, and rules have to be written as expressions, and now maybe you have variables and conditions and so forth, and before you know it, you've sort of come up with a bit of a bastard programming language in your DSL. So quite often these things evolve in odd ways and are not very well thought out. There are some companies in the industry, though, that are trying to really sort of capitalize on this. A company called Intentional Programming that was founded by Charles Simoni, who previously was at Microsoft. There's a company called JetBrains that have an MPS programming system, and more recently, Microsoft has this Oslo project, and in the Eclipse world, there's a lot of talk about a thing called Xtext. So a bunch of folks are trying. I wonder, when I look at external DSLs, I do wonder how much room there is between these languages with their own syntax and, for example, XML dialects. It seems to me that using XML dialects, you can leverage a bunch of tools and sort of get there a lot quicker than having to define your own syntax and whatever. Okay, so internal DSLs are, like I said, it's really sort of a fancy word for APIs and their usage patterns. Here are some examples. Up here is Link, Ruby on Rails, and some jQuery code. And what sort of characterizes an internal DSL is that it's just an API and the way you compose the API. And then if you squint, you can sort of pretend that there's a little domain-specific language there. Internal DSLs, most of them use this fluent trick of dotting together methods, as you see with Link here, for example, where you do .where, .orderby, .select, and whatever. The same with jQuery. Many of them use metaprogramming. If you look at the Ruby on Rails example, there's a bunch of metaprogramming going on there. But what characterizes these DSLs is that in them, you can access the host language's types and variables. You get access to statement completion and refactoring and all of the sort of things that are available in the host language. Now, I thought I would just spend just a couple of minutes showing one example of a DSL that I worked on called Link. That I'm sure a few of you have already played with, but let me try and just give you a quick idea of what I mean by programming in a more declarative style. Here I have a little program that just dummies up a bunch of products, and then it puts it in a data grid that it data binds to. And let's say I wanted to take all of the products whose price is greater than 20. Now, traditionally, I would write it like this. I'd new up a result list, and then I would for each on my products, and if the unit price is greater than 20, then I'd add it to the result, and then finally I'd show all of that, or I'd data bind to that. And if I run this program, here's the result that I get. Now, let's say that I wanted to do something a little more complicated here. Maybe instead of showing products whose price is greater than 20, maybe I wanted to count or gather up the categories of those products whose unit price is greater than 20 and maybe count how many products are in those categories and sort them by how many products. Now, in order to write that without a domain-specific language, I would first maybe declare a class that represents my result, which has category name and product count. And then I would have to write some sort of pretty ugly code, maybe like this, where I first new up a dictionary, that goes from product name to, or from category to a grouping object. Then I iterate over my products. If the unit price greater than 20, then, well, if I hadn't made a group for it yet, then go make a group and set the count to 0 and then increment the count. And then once I put them all into a dictionary, then I got to sort the dictionary. In order to do that, I got to give a delegate sorting function and blah, 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 blah. If I run it, I certainly get my result. But let's say I now, first of all, this code would take a little while to write, obviously. And it's, as you can see, it's very much about the how. And the what has sort of gotten lost, right? Let's say I move on and another programmer comes in and has to maintain this code. It's going to take a little while to at all understand what's going on here because you can't see the forest for the trees, so to speak. Now, if instead we use something like a domain-specific language like Link here, we can get rid of all of this code and boil it down to just this, products, where, blah, 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 group by, order by, and so forth, because we have a domain-specific language that allows us to talk in higher order terms about what it is we want done. And all of a sudden, out of the fog here, sort of comes more of the what and less of the how. I'm not here saying exactly how I want to go about filtering. I'm not saying that I want to make a dictionary to make the groups. I'm saying I want groups. And then the infrastructure can be smart or smarter about how it does this. Indeed, it's not very hard to imagine running this concurrently because I haven't specified the exact solution to the problem. Rather, I've just stated my intent. Let's just try and run it and see that, sure enough, we get the same result. Now, the thing that's interesting here about how these internal DSLs affect programming language design, if you look at what we ended up having to do to C# in order to make this possible, we added in C# 3.0 a number of features like lambda expressions and extension methods and type inference and so forth. And together, all of these features make it possible to design richer styles of APIs that you can then compose together to form internal domain-specific languages like the linked query language. Now, one of the things we also did actually was we added manifest syntax for these linked queries. So you can write it like the API style, but you could also write it like so. And indeed, the compiler simply translate this up here to this form down here. But I think what's interesting about this is that you can actually create a complete query language without doing anything to the main programming language itself. And we can sort of, because the language gets richer with all the things we've added, it now becomes possible to write richer kinds of APIs. And then if those APIs become popular, then we can add syntactic veneers on top of them like we did with Link, for example. So I'm very much a fan of that style of try first and buy later language design that we enable in that manner. Okay, let me get back to, whoops, not this one, but here. So the other thing I talked about, the other sort of thing that's important in declarative styles of programming is functional programming. Functional programming has actually been around for a mighty long time. One of the earliest programming languages out there called Lisp is a functional programming language, and since Lisp we've seen other functional programming languages like APL and Haskell and Scheme, MML, and so forth. And there's actually been a lot of research on functional programming languages in academia, and in the last, I'd say 5 years or so, 5 or 10 years, we've started to harvest a lot of the results of this research and put it into more general purpose programming languages. And today, I would say languages like C#, Python, Ruby, Scala are all heavily influenced by functional programming. I thought I'd take just a few minutes and give you my sort of layman's introduction to functional programming. I find that a lot of people have heard about functional programming, but they're not quite sure how is it different than regular imperative programming. So let me try and take a crack at that. Now, when we write programs with our imperative programming languages today, we often write code like this, hey, x equals x plus 1. And really, one of the things that we rely on very heavily is state, mutable state, or variables whose value can change over time as the program runs. And mutable state is very powerful, but along with mutable state comes the problem called side effects. When you have mutable state, your program can have side effects. In your programs, you can, for example, have a void method that takes no arguments, yet it can matter to the program when you call this method and how many times you call it and on what thread you call it, because the void method can, behind the scenes, make changes to state. And that, in turn, can affect what then further happens in the program. Now, in a functional program, this is not the case. In a functional program, all state is immutable. You can make state, but you can't change it once you've made it. And because you can't change it, you basically, in a functional program, don't really have variables. You just have names for values. If I go back to my analogy here again, actually, functional programming, I would argue, is more like math. It's more like equations than it is like program statements. If you take my x equals x plus 1 up here and you show that to a programmer, he goes, of course, you're incrementing x. If you show it to a mathematician, he'll go, I know of no x's for which this is true. However, if you show him this, he goes, y equals x plus 1. Oh, yes, you're giving the name y to the computation x plus 1. You're just giving a name to that computation. And it's a very different way of thinking about it. This is not a variable called y. This is just a name for x plus 1. But its value isn't going to change from here on. Y is always going to mean x plus 1. So in a functional programming language, when you write functions, they can take arguments. When you call a function, all that you can vary in a function call are the arguments that you pass to the function. And all that you can get back from that computation is the result of the function. There's nothing in a pure functional programming language that the function can do to make magic changes behind the curtain. It can only use the arguments and return you a result. So in a sense, in a functional programming language, a void method is nonsense. All it could serve to do is make your CPU hot. It can't give you anything back. It can't have any side effects. Now, you could argue that how hot your CPU gets is a side effect, and you could measure that, but let's not get pedantic here. Point is that you sort of program in a very different manner. Let me try and sort of put it in code. My analogy is writing in a pure functional programming language is sort of like writing in, say, C# or Java with read-only and final variables only. So here's an example of a point class. First, the red one is the sort of traditional imperative of writing it. I might, in my point have an int x and an int y and a constructor, and then let's say I have a move by method that can move my point by some delta. And it does so by mutating that instance of a point. And that's all good and well, but what if I make an instance of a point and I now start sharing it? I give it to 3 different APIs or whatever, and then I go modify my point. Who's going to notify them that that state changed? Or now, maybe I have to have events then or whatever, but what if I don't have events? And then all of a sudden I have these unpleasant side effects that start to make my program go cockeyed. Now, contrast that with the functional view of it. In a functional program, you can have state in your point, like your x and your y, but it's read-only in that. You can initialize it and then you can't change it again. So the move-by method can't change the point. It has to make a new point and return it. It's a function that makes a new point, right? And now it's up to the caller to decide whether to hold on to the old point or the new point or whatever. But there is no chance of side effects here. And this goes deep, actually, in functional programming languages. It's not just my point class here. It goes into collection classes, sets, maps, dictionaries are all immutable. In a functional programming language, when I add an element to a list, I get a new list that has that element added, but the old list is still there without the element. And of course, the way data structures get implemented is profoundly different. You have to pick very different internal representations to make that efficient, or try to make it efficient at least. Now, some of the advantages then of functional programs is that as you can see, sharing of state is safe in a functional programming language. Because the state never mutates, I can freely share it. I can give any number of people copies of my point or my list here, and I don't have to worry about side effects. It's much easier to parallelize functional programs because I'm not running around modifying the states, and it doesn't matter how many threads there are and whatever, because the state is safe to observe. And indeed, if 2 functions are independent of each other, they can be executed in parallel or sequentially. It doesn't matter. We get other things like lazy evaluation. We can memorize function results. There are all sorts of interesting, desirable aspects of functional programming. And so you're going to ask, well, so why don't we all write our programs that way? Well, because at the end of the day, As I said earlier, it's not enough to just make the CPU hot. You gotta somehow present the results of your computation, and even putting stuff on the screen, in a sense, is a side effect, or writing it to a file, or sending it to an HTTP socket, or whatever. So functional programming in the real world is actually very much about writing islands of functional purity and then more tightly controlling the side effects. And there are really no pure functional programming languages. All functional programming languages do have side effects and imperative capabilities, but they differ in that they default to being functional. In a functional programming language, everything is immutable by default, and you have to do extra work to be mutable and to do the dangerous side effects, so to speak. So it's, in that sense, a different mindset, if you will. An interesting development in our ecosystem is this new functional programming language called F#, which is included in Visual Studio 2010. F# sprang out of Microsoft Research in Cambridge. It's architected by a fellow named Don Syme, who's been working on it for the last 5 or 6 years. It comes from it shares a common core with a functional programming language called CAML or OCaml. So it's characterized by being a strongly typed, very succinct language that supports pattern matching, type inference, and all of the things that sort of characterize modern functional programming languages. And then on top of that, F# adds things like async workflows and units and measures and other very sort of forefront language features. I'd say that the thing that's really a first for F# is that, to my knowledge, it is the first time that we've seen deep integration of a functional programming language with an industrial strength framework and tool set like .NET and Visual Studio. And F# allows you to use all of your .NET framework. All the classes in the .NET framework are directly usable from F#, and F# very much has the execution profile of C#. It's strongly typed, it produces very efficient code, and so forth. I thought I'd give you just a little demo of what it looks like to code in F#. Let me try to open this up. And I'm going to start by opening up one of my favorite F# features, the interactive prompt. But then I will also grab this file here. So F# comes with an interactive prompt that allows you to just type code and have it execute right away. For example, here's the value 5. Let's say let x equals 5. And now I've created a value x, a variable x whose value is 5. I might say let square of x equals x times x, and now I've defined a little function called square, and now I can say square 5 or square 10, and so forth. So F# allows me to be very dynamic in my usage. However, it is actually a strongly typed programming language. And we'll try and take a look at that. Let's say I wanted to write just as an example here, a function that computes the sum of the squares of the elements in a list. So it iterates over the list and squares each element and adds them up to form a sum. And let me try and write it first in the imperative style and then in the functional style, and you'll sort of see the difference between the two. Here first is the imperative style, and you'll see that I create myself an accumulator, set it to 0, and then I loop over my list L, and I add to the accumulator the square of each element, and then finally I return the accumulator. Now, a couple of things stand out. First of all, notice how, in order to have mutable state, I must specifically declare it to be mutable. So the default here is immutable, and unless I do extra incantations, I can't mutate state. The other thing you'll notice is that I never said anything about types in this program. You'll see how it's very, very dense and succinct. Yet, if I hover, it'll tell me here that sum squares I is a function that takes a sequence of ints and turns it into an int. And then you go, well, where did the int part come from? Well, it comes from type inference. Indeed, the compiler infers from this 0 here that accumulator must be of type int. And because accumulator is of type int, then this must be a plus of 2 ints, and that means square must return an int, and that means blah, 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 blah. And so it spreads out, and it basically infers ints everywhere. If I go and change this to a floating point value, and then hover again, you'll see that all of a sudden now this became a function that takes floats and returns floats. So very strong type inference here, yet it is very, very succinct. I can just press Alt-Enter on code in the editor and have it execute down here in the interactive, and now I can call sum squares I of, say, the list of the numbers from 1 to 100. There. Now, let's say I wanted to write this in a more functional style. Here's an alternate version of it that's written in a pure functional manner. And this, you'll see, once you understand what it means, is much more like math in a sense. So here I define my sum squares over my list as match the list with the following patterns. If the list is empty, then the result is 0. Otherwise, match the list against a head and a tail. So break it into a head and a tail, and then take the square of the head and to that add sum squares of the tail. So recurse over the rest of the list. So here you see that I managed to compute the sums of the squares without ever changing the value of a variable. I only create new values. And the trick I use is recursion. And just like math uses recursion very often in formulas that break down to just the few sort of variations that exist and then recursively defines itself, so do you use recursion in functional programming languages. And the compiler then does a lot of work to try to turn the recursion into tail recursion, which means iteration and so forth. So if I, let me try and select this. Again, press Alt-Enter. And now I can do, not up there. I can down here do sum squares f of 1 through 100. And I'll get the same result. Now, of course, you're typically not going to write your code like that. You're more likely just gonna use higher order functions. So here, for example, I could write my functions as just take the map the x times x function over my list and then sum that up, and I would get the same result again. And that's probably more typical about what you would do. But I think the thing to sort of take away from this is that this language is very, very succinct and has sort of a very different feel to it. But nonetheless, it is a full-blown programming language that allows you to write code that's very similar in execution profile to C#. Okay, so that was a little bit about F#. Let me move on and talk some about dynamic languages, the other one of the three trends that I mentioned earlier. So again, I tried to sort of find a definition of what is a dynamic programming language, and again, it's sort of vague, but generally speaking, I think it's true to say that a dynamic language is a language in which there's no distinction between runtime and compile time. Unlike static programming languages like C#, where you first compile the code, and at compile time you get some errors, and then you run it later. In a dynamic programming language, the two are sort of intermixed. We're all familiar with examples like JavaScript and Python, Ruby, Lisp, and so forth. Now, dynamic programming languages have some advantages that I put in one column here, and static languages have other advantages. And there's sort of been this tug of war between the two camps over the years. And honestly, I think that the answer is neither one nor the other. Both really have desirable qualities. And I think longer term, the answer is a hybrid that merges both. And I think that's what we're seeing gradually in programming languages. The two disciplines are merging. Now, dynamic programming languages sort of have been characterized, or a lot of people think of dynamic programming languages as being slow, and there's lack of type safety and so forth. And so I thought I'd just sort of take a look at and contrast what it is that's qualitatively different about a dynamic programming language and a static programming language. Here's a piece of code that actually, interestingly, is syntactically correct code both in JavaScript and in C#. And it's interesting to contrast how the two languages treat this code. If we first look at it as C# code, and what this code just is, it just sums up a bunch of ints, in a for loop. Like normally you wouldn't do this, but it's just an example. So in C#, when I use the var keyword, it actually means please infer the type for me here. And so the compiler will here infer that A and I are of type int. And when I run this code, my A and I variables are just 32-bit or 64-bit if you're, 32-bit slots on the stack. And the inner loop of my for loop here just boils down to a simple add instruction, really. And it can run very, very efficiently. Now, if you look at the JavaScript, or the dynamic language view of this same code, well, in a dynamic language, or in a language with dynamic typing, var simply means a value. It could be a value of any type, and we don't know what type it's going to be. So when I say var A and var I, what I actually get is like a dynamic variable that has a type tag that tells me what the current runtime type of this variable is. And then in this case, it might be int, and so there's room to store an int. But sometimes it might be a double, so there has to be more space to also store a double, or maybe it's a string, and you have to store a reference to a string, and so forth. So immediately, one thing you see that's different between the two is that variables are more expensive to represent in a dynamic programming language. There's a lot more overhead. And because space equals speed in today's CPUs, if you have variables that are bigger and you have arrays of them, then it takes longer to process them. And so some efficiency is lost there. Also, in JavaScript, when I evaluate A plus I here, for example, that evaluation isn't just a simple add instruction. It has to first load the type tags of the two variables, then based on those, select an appropriate add operation, then load the two values, then do the add, and then check whether the add overflowed, because in JavaScript, if it overflows, then it becomes a double, and then we have to do some other things. And so there's a bunch of overhead here as well. And then typically, dynamic languages often are run by interpreters, so there might actually be bytecode that's being interpreted. And when you sum all of this up, you can end up with, a hit that's up to 10 to 100 times slower to run the code. Now, things, however, have gotten a lot better for dynamic VMs and engines over the last few years. If we sort of start out with the classic view, say this was IE6 or IE7, where we have a pretty slow traditional interpreter in there. Well, the reality is that today, most JavaScript engines now have JIT compilers, and so we've gotten rid of the interpreter overhead, and that brings down, the aggregate loss there to the 3 to 10 range. But over the past few years too, our JIT compilers have actually gotten remarkably efficient. There's this whole new generation of adaptive JIT compilers in browsers like TraceMonkey and V8 and now in IE9 we have the new Chakra engine that some folks are building at Microsoft, and these adaptive JIT compilers use interesting new developments like inline caching and type specialization, hidden classes, tracing, and whatever to get the overhead down in the 2 to 3 range. It's actually pretty amazing how efficient they've gotten. Now, I do think that we're sort of in the JavaScript engine wars. We're starting to reach the the max possible equilibrium there. I think that there's only so much more efficiency that you can get out of them. But I do think it's true to say that today JavaScript has gotten efficient enough and is ubiquitous enough that it really is the language that rules the web client. Now, that said, JavaScript was never intended to be a language for programming in the large. And interestingly, there are some interesting tools out there, like the Google Web Toolkit, or we have a guy named Nikhil Kotari at Microsoft has created this thing called Script Sharp, which allows you to write either in C# or in Java, and then have your code compiled into JavaScript, which then it's almost like using JavaScript as an IL. The whole Google Wave project is written using the GWT, and the team swears that they couldn't have written it in JavaScript because it's simply too complex. So there's some interesting developments going there. I don't know exactly where it's going to end up, but I think for programming in the large, JavaScript is still not quite there. But whether the solution is to do coding in Java and C# and turning it into JavaScript, I don't think that's quite right either. So we'll see where that all goes. Now, for dynamic programming on the .NET runtime in .NET 4.0, we're introducing this a new feature called the Dynamic Language Runtime. Now, the way to think about this one is that where the CLR is about creating a unified framework and programming model for statically typed programming languages, the DLR is about creating a unified programming model for dynamic languages on the .NET platform. The CLR has had support for dynamic capabilities like reflection and reflection emit and so forth, but in order to implement a dynamic language on top of .NET, there's a bunch of stuff that you would have to do over and over. And in order for dynamic languages to interoperate with themselves and with static languages, there was a bunch of features that were missing, and that's sort of what is embodied by the dynamic language runtime. It has features such as expression trees, efficient dynamic dispatch, call side caching that makes your dynamic code run efficiently. And in .NET 4.0, we now use the dynamic language runtime for not just Iron Python and Iron Ruby, but also C# 4.0 and VB.NET version 10. Use the dynamic language runtime to do their dynamic dispatch, and so we get a shared implementation of all dynamic capabilities, and we can interoperate between all of these languages, and then dispatch to a variety of different technologies, either be that .NET or in Silverlight, talk to the JavaScript DOM, talk to Python code, talk to Ruby code, talk to Ole automation servers like Office and so forth. Okay, another key sort of interesting thing about dynamic programming languages is metaprogramming. And metaprogramming is really a fancy word for code generation, if you will. It's something that we rely on, day to day in our applications. And it's interesting to look at why it is that dynamic programming languages are very well suited for that. So in this little blue box here, I have some Ruby on Rails code, and basically this declares an order class by inheriting from active record, and then it defines a couple of relationships, a belongs to and a has many relationship. And key to dynamic languages like Ruby is that everything executes, even class declarations are executed. And when this class declaration executes, it makes calls to a belongs to method and a has many method. And the belongs to method then reflects on the code and injects all of the patterns necessary for a one-to-many relationship and a one-to-one relationship. So in a sense, the code is dynamically generating itself as your program runs. And of course, that's a lot easier to do in a dynamic programming language because there's no distinction between compile time and runtime. Now, static programming languages have a harder time of this. You know, when you use OR mappings in, say, C# or Java, you typically have to run a code generator that looks at your database and generates a whole bunch of source code that you then have to compile, and it's kind of clunky. Now, over time, I think this will get better. One of the ways it's going to get better is this thing that we're working on called that we call compiler as a service. And let me talk a little bit about what that is. Now, traditionally, compilers have kind of been like black boxes. You know, on the one hand, you feed them source file, and then out the other side come .NET assemblies or object code or whatever, and then whatever happens inside the black box is sort of magic, and you don't get to participate or understand what goes on. Yet, if you think about it, increasingly, code isn't necessarily stored in source files. Like if you want an interactive experience, like an interactive prompt, you know, well, the code isn't in a source file; it's being typed in by the user. If you're implementing, say, a domain-specific language like Windows Workflow or BizTalk or whatever, where you have little predicate rules that are, say, written in C# or VB that you want to evaluate dynamically, well, they don't sit in source files. They sit in like XML attributes or whatever that you want to fish it out and somehow get it compiled, but you can't because you have to first put it in the source file, and that's sort of a complicated thing to do. And likewise, on the other side of the equation, increasingly it's true that from the compiler we don't necessarily want assemblies. We may want a more tree-like representation of the code. If we want to, for example, implement user-written refactorings, we would want not an assembly, but rather a parse tree of the code so we can reason about the code and rewrite it and so forth. So more and more, we sort of see a need to open up the compiler and make an API out of it, where you can actually give it a little piece of code and get it compiled and then get back either code you can execute or a parse tree that allows you to reason about the code or rewrite the code and so forth. And by doing that, we can enable a bunch of interesting capabilities in our statically typed languages like metaprogramming, like a full fidelity language object model, and so forth. And that's something we're working on, and it's something that I'll talk about a little bit more in my C# 4.0 talk later this afternoon, I think at 1 o'clock. Okay. Last thing I wanted to touch on is concurrency. Now, by show of hand, how many of you are familiar with Moore's Law? Pretty much everybody. And how many of you have heard that Moore's Law is come to an end? Yeah, I see a lot of people. Well, I've got good news and I got bad news. Moore's Law has not come to an end. Moore's Law says that the number of transistors you can inexpensively put on an integrated circuit doubles about every 24 months. And it has, interestingly, remained true since the mid-60s up until now. And by all projections, this is going to remain true for, as far as we can see, the next at least two decades from now. Now, alongside with Moore's Law, we have had another interesting phenomenon, which is the doubling of clock speed that has happened about on the same schedule. Every 24 months or so, we've gotten CPUs that go at about twice the clock speed. But that has come to an end. Let's do again, by show of hands, how many of you have 20 gigahertz CPUs in your machines? See, nobody. But if you had projected the curve from about 5 years ago, we should have all had 20 gigahertz CPUs today, but we don't. About 5 years ago, it stopped. In fact, it peaked at 4, and then it sort of went down to 2 or 2.5 again because we can't get rid of the heat, and they suck up too much juice, and they run down the battery too fast. So we've run up against some fundamental laws of physics there that that put an upper cap on how fast we can make our CPUs. However, Moore's law, in a sense, comes to the rescue because we're still seeing an increasingly an increase in capacity, and so what's happening now is that we can put more CPUs on a single die. You know, today it's like dual core, quad core. Intel CTO said here 3 years ago that we should easily be able to hit 80 cores within the next decade. And with 80 cores, then soon you'll be looking at this when you bring up Task Manager. And that's a scary thought there. You know, it's in fact, this is a 128 core machine that we have in our lab. This thing actually exists. It is not often in the fully utilized state that you see here. In fact, and that's part of the problem, right? Let's say that you take one of your traditional apps and you run it on this phenomenal machine. Well, you'd be happy to see 1% utilization, right? Because traditionally our apps just run on one core. So the challenge that we're faced with is that we have to write our apps differently in order to take advantage of this coming kind of machine. Herb Sutter, a coworker of mine, put it very succinctly in an article he wrote. He says, the free lunch is over. And it's true. You know, we have become accustomed to sort of writing our apps and, hey, if they turn out to be slow, it's fine. Well, just wait for the next generation of hardware and then that'll take care of it, right? Then it'll run faster. Well, no, it won't. Not unless you write it differently. Indeed, this is both a challenge and an opportunity. You know, it's a challenge because concurrency is hard. And we don't really have an easy answer to concurrency today. We're getting better at it, and I'll show you some of the things that are happening. And it's an opportunity, of course, because on a box like this, if you can actually harvest all these cores, you could have 2 orders of magnitude performance improvement. But it needs to be done differently. You know, the thing that's interesting about the many-core revolution is that it really sort of makes us think about a different kind of concurrency. Traditionally, concurrency has been about running multiple logical tasks on a single CPU. So a multitude of tasks on one CPU, the old time-sharing or time-slicing model, right? But if you think about the kind of concurrency we have to deal with now, it's exactly the opposite. It's about running one logical task on multiple CPUs. And that changes how we write our programs. That means that in our programming languages and APIs, we need ways now to decompose our application, to break it into a multitude of small tasks that can be executed independently. And that's something that hasn't really traditionally been present in programming languages. Now, doing that with today's concurrency APIs is hard. Like if you do it with threads and thread pools and monitors and locks and whatever, you're not going to get very far. Luckily, you know, these APIs are evolving, and one of the sort of nice things that's happening in .NET 4.0 is this thing we call the parallel extensions for .NET, which in a sense is a modern concurrency library that separates you the logical notion of concurrency from the physical sort of level that we tended to be at. You know, previously our APIs dealt with things like threads and whatever down at the orange level, but with the task or with the parallel extensions for .NET, you get to deal with it in a more logical fashion. You know, you have the task parallel library, parallel link and coordination data structures that allow you to just reason about logical units of work, but not have to reason about how they execute and on how many threads and how many CPUs and so forth. I thought I'd give you just a brief demo of what that looks like in action. Let me try to bring up a little P-Link demo here. Here's a little program that that reads in an XML file. In fact, let me try to open it up. It's popularnames.xml here. That's a 50 megabyte XML file that contains data scraped from the Social Security database in the US that gives you statistics on what names were popular in what years, in what states, and so forth. Now, this program that I have here reads in this XML file, turns it into a list of, where's my type at here? Whoops. There's something missing from it here. Let me just try to do something here, sorry. There. Copy this, paste it here, okay. It loads up that XML and turns it into a sequence of objects, put them in a list, and then it runs a link query over the popular names here, looking for all Roberts in the state of Washington, and counts up, orders them by year. Let me try and run it, and you'll see sort of that it first loads the 500,000 XML records, and then runs the link query, and it takes a little over 2 seconds. Now, one of the things I can do with plink is I can try to turn this query into a parallel query. I can just copy it, and then let's say query parallel here. And then all I do is I use the asParallel extension method on my source that I'm querying, and that introduces a different type and a different set of extension methods for link that now will actually use a parallel implementation of all the same operators. And now let me try to run the two back to back. So first I'll do the sequential one, then we'll do the parallel one. And here we'll just run query parallel to list. And let's try and run this. And you'll see we load the XML data again. 500,000 records. It takes about 2 seconds sequentially, and it takes about 1.5 seconds. Well, let's try and run it again. I usually get a little better result than that. There may be some background task running, so let's see if we can get a little better. Usually get about linear speed up. This is a little closer to it. So here you see that with not a lot of work, I could actually harvest some of this concurrency that's available. This is a dual-core machine that I have here. Now, I don't want this to come across as me selling snake oil, that all you just got to do is say asParallel, and then magically everything runs twice as fast. Obviously, sometimes it doesn't, and sometimes queries can't be parallelized, or at least maybe they can't be parallelized as effectively as this. However, I think you'll agree with me that by writing your code with a domain-specific language like LINQ, you can see how it is certainly more possible for us to help you run this code in parallel, and certainly you stand a much better chance of harvesting some of this concurrency. And indeed, it may not work every time, but at least it's a lot cheaper to try. Imagine if I had written this as a normal app with for loops and whatever, and now I had to put a thread pool in there and start threads and whatever. I could get myself completely lost in those APIs, where here I can just try it and see if I can gain some advantages from it. Okay, so of course, You saw me do it with a link query here, but another big generator of work in today's applications is loops. If you think about it, where does the majority of the work in an app come from? Well, it comes from your loops, right? Where you're looping over data. And in cases where you have loops that do independent work for each iteration, there is an opportunity to harvest concurrency. So if you have in your app loops that do independent work for each iteration, and I know that that's an if, but in a lot of apps it happens. Then with the task parallel library or the parallel extensions for .NET, we have new APIs that allows you to turn those into parallel loops. You can simply almost like refactoring your for loop into a parallel .for with the same body. Or if you had a for each, you can do a parallel for each. Or if you have a bunch of sequential statements, you can do a parallel invoke of those. And the task parallel library will then take care of running these pieces of work on as many threads as are optimal for the number of CPUs you have, and so you don't have to concern yourself with the sort of deeper parts of it, but rather you can focus on writing the logic. Now, as I said, this is if you know that you have independent pieces of work, but often they're not, and there's a lot more that we could do in our programming languages to allow you to reason about these things. For example, things like isolation. How do I know, or could the compiler check for me whether this piece of data is isolated and is safe to run concurrently? Or when I new up objects, as long as I haven't shared them with anybody else, it's actually safe for me to mutate them. But once I start sharing them, then it becomes unsafe. So is there maybe something we could do in the type system to track whether you have shared the objects, like linear types or whatever that is some of the research going on in academia? We could do better about allowing you to reason about purity in functions. How do I know whether a function has side effects? Is there something that the compiler could do to check it? And if so, then it could, disallow me from doing parallel things unless my functions are pure. And again, immutability. Today in C# and VB, you have to do extra work to make your objects immutable, and it really shouldn't be like that. We ought to have better support in the language for immutability, and so those are all things that we think about because of concurrency. I would say that in terms of what language features we're actually going to make out of this, the principle we go by is that don't expect to see, a particular concurrency model put into C#, because there are many different kinds of concurrency. Rather, it's more about finding things that are common to all the different kinds of concurrency, like isolation and purity and immutability, and then adding those to the language such that you can build different APIs that then encapsulate the different kinds of concurrency, yet take advantage of these core language capabilities. Okay, that is, I think, the end of it. Let me try and wrap up with some conclusions. I think, for programming languages, these are interesting and exciting times. There was sort of a strange doldrum period for programming languages between 95 and 2005. When Java first came out, it really just sort of flattened the programming language space, because everything was going to be Java. My God, it was game over for programming languages. We were done, and gradually we all sort of discovered that, well, maybe that wasn't, the end-all be-all, and now we're sort of back and seeing lots of flowers blooming, lots of interesting languages being built, and I find that very exciting, because, new languages is how we make progress in the business of programming, and so the more the merrier, in a sense. If I had to recap where I think languages are going to be in the next 10 years, I think, first of all, I think languages are going to be more declarative. We need to work on introducing capabilities like meta-programming, functional programming. We need to find perhaps ways of allowing users to extend the syntax for domain-specific languages and so forth. I think in 10 years, the distinction between dynamic and static programming languages is largely going to be gone. The two will have merged into a common single paradigm. And I think, in the area of concurrency, we'll see languages adopt capabilities that allow you to reason about things like isolation, function purity, write immutable data structures better. In sort of to wrap it all up, I think the way I would characterize it is that for programming languages, the new paradigm is going to be multi-paradigm programming languages. And that's the end of my thoughts about programming languages here. I hope I didn't bore you too much. And if you're interested in hearing more about C# 4.0, I'm giving another talk on that today at 1 o'clock. And with that, I thank you for being here and hope you enjoy the conference. Thank you. Thanks.
Ladies and gentlemen,